The next installment of this series of logarithmic questions comes from question number 6 from your logarithm review guide, and it deals with caffeine. And so I want to talk about caffeine. Caffeine is actually a drug. It's an addictive drug. You start drinking caffeine and it affects your body in different ways, changing your hormone levels, and you can get addicted to caffeine. So be careful with it. All right? But what I want to talk about is how much caffeine remains in your system after each hour you ingest it. There's a statistic that shows that 75% of caffeine will remain in your bloodstream 1 hour after ingestion. After every hour, 75% of the previous hour still remains. So we have an exponential decay happening here. 75% remains, 25% decays away. So I'm going to set up a problem that deals with an initial value of 40 milligrams of caffeine. All right? So if you start with 40 milligrams and we decay 75%, what I want to do is put this into an exponential equation, exponential decay equation. Now, side note on that, all exponential functions take on the form a times b raised to the x power. A is your initial value. On a graph, that would also show up as your y-intercept. When the x value is 0, this turns into 1, leaving just your initial value, or your y-intercept. And then b is known as your rate. Now, that rate is always in decimal format, not a percentage, and it also can be growth or decay. Growth if you're greater than 1, and decay if you're between 0 and 1. Keep that in mind. We start setting this up into that format. The initial value of 40 milligrams goes there. Our rate is dependent upon our 75% decay. That as a decimal is 0.75. And we can use an x or a t depending what you prefer. I'm going to use t to represent time. And since we are dealing with a function rule, I think I'll change this y to indicate function with caffeine. So I'll call it c of t, the amount of caffeine in our bodies given a certain time. So this is our exponential we're dealing with. What I might ask you then is say how much caffeine is in the system after so many hours. For instance, I might ask, what does c of 1.5 mean, and what is that value? Well, 1.5 would be 1.5 hours. And if you put that into our function rule, 0.75 gets raised to the 1.5 hours, and you'll come out with your caffeine rate. Well, after 1.5 hours, this approximates out to be 25.98 milligrams. So that's the kind of question you would answer if I'm asking you how much is left at a given time. Well, in contrast to that, what if I ask you how much time it takes to reach a certain amount? The famous question we ask for decay is, how long does it take this substance to decay to its half the substance amount, or its half-life? So if I ask you to find the half-life of caffeine, I'm asking for which this value turns into half of the initial. Our initial amount is 40, so if I were to ask you a question like that, I would say 20 has to equal 40 times 0.75 to the t power. You need to solve this for t to find the half-life, the time to reach 20 milligrams. So to solve this problem, I'm going to have to use some inverse properties. The first thing I have to do is I have to try to isolate t. To isolate t, I have to undo the order in which I would solve. Well, in the previous problem, using the order of operations, I had to raise my power first and then multiply by 40. So to solve, I have to undo that order as well. I begin by dividing by 40, thus showing the 20 over 40 being 0.5, half-life, right, would equal to our rate, 0.75 raised to t. Our next step, however, is to solve for t using the inverse operation to base exponentials. 0.75 is our base. Let's use a logarithm that's based 0.75. We can do that on our Inspires, and if you're not using a TI Inspire, we can still do this on the 84s or a prior calculator that only has base 10 exponentials. I'll show you that second. What I want to do is use a logarithm with the same base as this exponent. So logarithm base 0.75 of 0.5 would equal the logarithm of 0.75 to the t power. The reason I chose this logarithm is because of its inverse. So these are going to be inverted and give you t. So I'll write that up here. I now have the logarithm of base 0.75 of 0.5 equals t. If I find this value, I'll find that the time is approximately 2.41 hours. Well, in addition, I want to show you how to do this calculation if you're not using an Inspire that allows us to change the base, or the 84 that allows us to change the base. You can use a common logarithm. So I kind of reapproach the problem as it was. 0.5 equals 0.75 raised to the t. If you use a common logarithm to solve this, common logarithm base 10 of this side, and a common logarithm base 10 of the other side, our power property says that this t now can come in front of the logarithm. This is just a number now, log of 0.75, and this is a number. So it's a number times t equals this number. We're going to solve for t by dividing by this log of 0.75. This setup shows just the use of common logarithms. In fact, a shortcut, if you want to use common logarithm and you only have a base that's not 10, is to take your base, if I have b to the x power, if I want to solve this, I can solve this, where it's equal to c. It's the log of c divided by the log of the base. And these are both common logarithms. That's a shortcut to help you as well.